tackling a range of geological depth conversion scenarios relevant to Latin America using VelPAK. Hi, I'm Kathy Cowley from Equipoise Software. We work in partnership with IHS Markit to develop VelPAK. The VelPAK model is designed to satisfy the velocity modelling and surface depth conversion needs of the seismic interpreter and experienced geoscientists alike. It enables you to make confident decisions on where to drill for oil and gas, quantify your uncertainty, and accurately determine the GRV range of your prospect. In this webinar, we will review several methods of depth conversion relevant to geological situations found in Latin America. The first part of the webinar will focus on deep water compaction with or without salt, where good quality seismic data means processing velocities can guide depth conversion either with or without sparse well coverage. During this part of the webinar, we will be utilising the VelPAK wizard to use stacking velocities in a number of ways, including production of pseudo wells to create a geologically reasonable velocity model that can easily be conditioned to any real well information available. The second part of the webinar will be to demonstrate VelPAK capabilities with regard to onshore complex structural traps where data is limited to 2D, and we'll have a quick look at the VelPAK capabilities for profile depth conversion of these complex data sets. Finally, the webinar will conclude with a demo of our HiDef module available from within VelPAK, which can be used to scale processing velocities within a geologically constrained model and create hybrid models for layers where processing velocities may be less reliable. So, for the first part of this demo, we will look at seismic velocities with or without sparse well coverage. We will look at three different techniques for combining seismic velocities with the well velocities, calibrating the seismic velocities to the few wells we have, and depth converting using the calibrated seismic velocities, using the seismic velocities as a drift surface to guide gridding of well velocities if we have 3 or more wells, and deriving velocity depth relationships from the seismic velocity traces, which may be a useful approach if we wish to extend the velocity model outside the area of our seismic survey. We will use a 3-layer model and use each of the above techniques on a different layer purely for demonstration purposes. Typically, seismic velocities vary significantly from the well velocity measurements, so if we are to take advantage of the consistent lateral control seismic velocities give us across our surveys, we need to calibrate them to the well velocities. There are numerous ways of calibrating seismic velocities to wells, but a simple and effective method is used by the wizard for direct depth conversion available in VelPAK. It is a 3-stage process, and just before going into the wizard, let's go through the 3 stages. First, if we are using stacking velocities, we convert them to interval velocities using the Dix equation. We do not need to worry about post-Dix anisotropic scaling, as this is done in the calibration, so the scaling factor is set to 100% automatically. We may then need to smooth the seismic velocities, especially if they are stacking velocities, as they are inherently noisy. We then depth convert using the seismic interval velocities to create a seismic depth surface. The isopachs from this layer are compared to the well layer thicknesses defined by formation tops, and an average calibration factor is computed. We also back calculate scaled interval and average velocity grids so that we are information consistent in the model. If we choose, we can finally compute the mistime between the well tops and the depth surface, generating a residual correction surface, and apply this to the depth conversion so the final depth surface is guaranteed to honour the formation tops. Note that we don't enforce a tie at the calibration stage, as it's not best practice to combine 2 independent variables in one surface, although the net result is the same. By dividing the procedure into 2, it becomes much easier to detect issues with outliers or bad data, which may be obscured if we try to do this all in one go. This all sounds like it might be a complex procedure, but the wizard tool within VelPAK makes this very easy. So let's have a look at the project we will be using in VelPAK before we go into the wizard. The project already has data selected for the model. We have a time grid here displayed on the surface module for layer 1, and these data are shown in the model tree to the left against each of the events. If we open up the surface part of the model tree, you can see the time grid stored under event 1. Also within this model tree you can see that we have the 3 wells displayed. On the surface display, if we change the display to basic rather than showing the shaded contours, we can see the wells more clearly. The pink dots display where the stacking velocities are over the area. And if I bring up the velocity module, we can see the RMS stacking velocities and corresponding average velocities ready to be calibrated. Now if you bring up the well module, we can see one of the 3 wells displayed here in depth. The layer definition for the well has been done as part of the data selection procedure via the link. The layer definition selection of tops relates the seismic pick to the geological top to associate the well formation top depth layers with the time grid layers. For every layer in the model that you have a time grid surface, a top is associated with it. The formation top denoting this layer is plotted on the left of the well display, for example Upper Triassic, and the corresponding seismic surface is displayed on the right of the log. So we can see at a glance that the grids correspond to the layer definition, or you may be able to see that within the 3rd layer here there is a slight discrepancy which we may have to look into later. So we have 3 wells, we have stacking velocities in the project, and we have time grids, so we are all set to go into the wizard. The wizard module allows you to complete often repetitive tasks quickly and efficiently for any given event in the model. The wizard screen starts with the help screen open at the bottom. Every wizard option has a comprehensive help within the window. In order for us to see exactly what is going on within VelPAK while we are running the wizard, I'm going to open various windows and dock them alongside the wizard. Like so, we can now see the wizard, we can see the well module, the velocity module and the surface module all at once. Before we start a depth conversion, we want to compare our seismic velocities with the real well curves we have in the project. We can look at pseudo wells that are generated at the real well locations, and if necessary run the Dix calibration factor on the seismic velocities to match at the wells. So if we press Run next to event 1 in the wizard, we will be presented with the options to work with and to choose from. The first screen is to select the method of depth conversion to use for the first layer, in this case seismic velocities. The wizard moves to the data verification page where it runs a check to make sure the data required for the particular process is available in the project. Press Next through this and we need to select the seismic velocity method we will be using. Here is a long list of depth conversion methods that use seismic velocities. In this case, however, to start with we are going to use the final option, generate pseudo wells from the seismic velocities. Note that the wizard here is acting as utility to do as it says and is not actually going to depth convert anything. So I select pseudo wells and the pseudo wells screen comes up where you can generate a set of pseudo wells over a survey location area or as a regular spaced array, and in our case at the real well locations. As I said, by comparing these with the true well velocity curve, we can see how useful seismic velocities might be, either holistically or per layer. Now this part of the workflow within the wizard works in conjunction with viewing the velocity module, so we must make sure the velocity module is on display. I'll make it a bit larger here. In the velocity module, the stacking velocities are shown in green, along with the average velocities that have been calculated via the Dix equation, as shown in black. You can already see that the average velocities do not lie directly on the green RMS velocities, so we may well have to apply a further calibration. There may or may not be a calibration factor required to apply to the generated velocities to calibrate them to the real well traces. This is what we will be doing next. So back into the wizard, we select Create Pseudo Wells at the same location as the real wells and press Create Pseudo Wells, And you can see that a pseudo well has been generated and laid on top of the well within the well module. A default percentage of 92% is used to start to produce a pseudo well at the well. Here you can see that for well 48.14.2 in Vision now, this scaling factor looks too high, since the stack wells look a little faster than the real well trace. So we can change the factor for event 1 to be, say, 90%. So if we go into the velocity module and set up the Dix flyout for event 1, return it to 90%. Press apply and then create the pseudo wells, and keep an eye on the pseudo well trace here when I press create pseudo wells. So that has moved the pseudo well to be more in line with the general trend for event 1. It's not going to be perfect. For layer 2 it looks like the pseudo well is slightly too slow for the real well, and certainly for layer 3 the pseudo wells are too slow. So we'll need to change the Dix calibration to, say, 94, and let's try 96 for layer 3. Pressing the apply and create pseudo well. Again, keep an eye on the well and see what effect that has. Layer 4, we're not doing a depth conversion in layer 4 today, but it is dragging in the velocity at the bottom of layer 3. So if I change that to also be 96, press apply, create the pseudo well, hopefully that will bring it out a bit. Okay, we'll leave it at that for now. And if we move through the other wells in the project, hopefully they'll look much the same. Yeah, they're okay. Note in the model tree that the 3 pseudo curves have been added as wells into the tree, with the name of the real well preceded by the word stack. So we have applied a calibration factor to the RMS velocities to try and tie them to the real wells, and we can now start depth converting. We will move through the wizard setup until we return to the wizard launch page by pressing next. And then when we press run again next to event 1 in the wizard, we will be presented with the options to work with and choose from. Again, we choose seismic velocities and move through the data verification page. And we need to select the seismic velocity method we will be using to depth convert. In this model, the stacking velocities are loaded, so the first 4 options could apply. I wanted to use the calibrated to wells and depth convert method, so I select that. In this method, a depth conversion is made by using interval velocities derived from the RMS stacking velocities. The ISOPAC of the depth converted layer is determined at each well location and compared to the well layer thickness based on the formation tops. A single scaling factor is determined interactively, and the interval velocity is then recomputed to best tie the wells. The calibrated interval velocity is used to re-depth convert the event. So I select that and press next. Now the seismic velocity grid is being generated. We are taken to the smoothing screen, which allows us to smooth the seismic interval velocity grid if necessary. The unsmooth seismic velocity surface is shown in the surface display and looks very noisy to me, with no apparent trend. There are 2 smoothing options that are given: a simple and fast moving average, or the more advanced multi-pass local regression option. For example, we can try both, starting with the simple moving average. I'll set a radius of, say, 5,000 meters for the moving average smooth, then press the apply button. We can see the smoothed velocity grid in the surface display. It is a lot smoother, but it can be smoother still, using the more advanced process of the local regression smoothing. This method, known as LOS for short, attempts to perform regression on noisy data, removing outliers from the data on multiple iterations. As such, it can give good results, though it is computer intensive and may take a few minutes to run. There are a few more parameters for this smoother, which we can adjust and see the changes. The help screen describes these parameters. though the most sensitive is the span value. I'll use the defaults and press apply. The smoothing takes longer than the moving average, and the large surveys can take some time. We can see the progress and estimated time remaining in the progress bar at the bottom of the screen. However, we end up with a result that is more closely resembling the input but smoothed. We can review the input data, which is stored in the model tree as stack interval velocity grid rough gridding of IV here. I can then redisplay the smoothed grid from the stack interval velocity smooth grid slot in the model tree to see the changes. I can tweak the local regression parameters should I need to, then regenerate the smoothed grid until I'm happy. But I'm fairly happy with the grid that I've got. Once you have designed a smooth velocity grid, we can press Next to move through the wizard. The curve display briefly flashes up and some processing is done. The wizard prompts us to apply the calibration factor. We can see what that is by looking at the curve display. The x-axis of the plot shows us depth, but that's not particularly interesting unless we have any outliers in the x direction. The y-axis gives us the calibration factor, that is, how much the seismic isopac needs to be scaled to the well isopac at each well location. So obviously 1 point per well. The mean of these scaling factors is computed as the horizontal line. The value of this is posted as the A0 value in the bottom right-hand corner of the display, along with the standard deviation of the samples. As with any other display, we can deselect and reselect individual wells by clicking on them. The mean value is dynamically recomputed. Just be sure that the selection is correct when you press the Apply Calibration Factor button in the wizard. The calibration factor is typically around 1. If values are much away from 1, check the units of the velocity and well data carefully. Note that this factor isn't directly comparable to a typical 5 to 15% reduction used for Dix conversion scaling, but it should be in a similar magnitude. When you press the Apply button, a preview of the depth converted grid is shown in the surface map. If the depth values look sensible, and they should, press Next on the wizard to move on to the usual residual error correction dialog. Because we have computed an average calibration factor for all these wells, there will still be misties for all the wells, and these are shown on the map here. It is better to calibrate to the mean, then apply localized corrections, than apply a regional grid that forces a tie but doesn't give any indication to problem data. So I'm going to just make localized corrections with a radius of 2000 meters of each well, so I specify the radius as 2000 and press the Generate button. I can adjust the radius as I see fit and press Generate again. When I'm happy with the correction grid, I press Next to re-depth convert, incorporating it. The wizard then comes to the Finish page after back calculating the velocity grids and the depth grid that tie with the well tops. You can see that the error is now greatly reduced. The final page of it for layer 1 here tells us it is finished and has named the setup we have just done, so we can see at a glance exactly what process we have done. There is also a space for your own comments about the setup here. Pressing Next again returns to the Launch page, and you can see that name appears in the Launch page under layer 1. All the grids that have been generated, including the velocity grids, are stored in the model tree as expected and can be displayed by clicking on them. So moving on to layer 2, this time we are going to use a seismic velocity process again, but a different one to the previous layer. So select seismic velocities and go through the verification page. This time we are going to generate an interval velocity grid, but not do a depth conversion yet on the layer. So we select under the Dix convert and use stacking velocities, generate an interval velocity grid, no depth conversion. Again, the process is making a rough grid of interval velocities. This bit is similar to the process we did in layer 1, but this time for layer 2, as defined by the layer definition shown in the well display. The smoothing page comes up, so we can immediately go to the low S smooth and get a smooth interval velocity grid. Once the smoothing is done, however, we move away from the method we used on layer 1 and move through the wizard back to the main wizard launch page. So far for layer 2 we have just generated a smooth velocity grid. and we're going to use that as an external drift grid along with the real well information that we have. So if we go back into the run for layer 2, and this time select mapping as the method. Press next and next again and select well vertical apparent interval velocities as the method for your mapping. Since we only have sparse well data, we will select the Kriging gridding method for our wells. The information has calculated a number of things, including an interval velocity grid using just the well information. But what do we do with this? Well, we can use the stacking interval velocity smooth grid that we've just generated from Dick's calibration. We can use this as the drift grid, enabling much more control over areas where the well information does not exist. So essentially we're going to merge the two grids that we've just generated for layer 2 together. Check the external drift box and be sure to select the correct smooth velocity grid from the list. The grid is generated and the depth grid for layer 2 is produced. As you see, there's very little error as you'd expect at the wells, since we have used so much control at the wells already. We will now move on to layer 3. We are going to use an optimization method for layer 3, which allows us to determine the depth conversion parameters from well curve or layer information using numerical optimization. These are processes based on the Mac-Al-Chalabi methods of trying to deduce the best V0 and K from the given parameters. Optimize uses nonlinear least squares curve fitting of time depth curve data derived from a range of sources, sonic logs, check shots or tops and times, to derive the best function parameters for each well. It has the facility for allowing one parameter to be fixed and the other mapped, for example fixed K and contoured V0. With close interaction between the parameter grid and the mapping modules, you can immediately see the V0 and K values that best suit your data. So we can make an array of pseudo wells over the entire survey area and then use this information in the fitting to time depth curves method. So firstly for layer 3 we are going to create the pseudo wells for seismic stacking velocities. So press seismic velocity, again select the generate pseudo well option at the bottom. So now we know that the calibration is correct for the wells, we can run a regularly spaced array or grid of pseudo wells using a spacing of 2000 across the area and an amalg radius also of 2000. This is the radius around each pseudo well that the process will gather the information to produce that pseudo curve. So when the process is finished, once you've pressed the button, you can see the grid of wells on the map. And again note that the pseudo wells are in the model tree. We can use these pseudo wells in various methods of depth conversion, but in this case we are going to use them in the optimize. So we move forward, pressing next to go back to the launch screen and press run on the layer 3 again. This time select optimize. Moving on, we get to the optimize method for event 2, so select the function to be optimized from the seismic datum and the optimization method to be fit to well curves. Press next and we come to the optimize parameter space page. Here the program has attempted to calculate the optimized parameter space, which is the range of V0s and Ks to examine, but the ranges can be modified here. After the Run Optimize action button has been pushed, you may interact with the Optimize module display to select and deselect wells or zoom in and out of the parameter space. So here we press Run Optimize and the optimization will begin. When the Optimize has completed, we can go into the Optimize module and have a look at the display it has generated. It looks a bit busy, but zooming in we can see that the pink are lines and each one represents the fit of a well for the layer. We can turn these line fits off to make the screen display a bit clearer. Now each point that you can see there refers to the best point fit of each well. Given the depth conversion parameters entered in the process, a grid is generated for each well in the model. The generation takes each pair of V0 and K values and works out the depth value, comparing it to the time depth curve data for that layer for that well. The value plotted is the difference between those two values, and as the value of V0 and K become more true, then the grid values will reach a low or trough, and contouring these values up will therefore show where the best values of V0 and K will be, and you can see the trough in the center of this optimized module display here. The optimum value V0 and K is shown within this trough as a fit point, in this case with a value of V0 approximately 3500 and a K of approximately 0.4. As you can see, these are the derived V0 and K on the wizard page. Now the optimizer has been generated, moving forward allows us to select what we want to do with these values. In this case we can use a fixed K and contour V0 method, which means for each well the V0 value corresponding to a fixed K is found from the optimization results and stored in the XYZ slot of VelPAK. A depth conversion intercept grid from these values using kriging is then produced. This introduces space variance into the model that is not present with the simple linear function V0K and is a good tool for predicting results away from the survey area. So I'll press Generate the V0 grid and display it. Pressing Next will do the depth conversion and we will have our depth layer for layer 3. So that actually concludes the depth conversion of the 3 layers using sparse data within VelPAK. We have the 3 depth grids that you can see in the model and you can look at them in the surface module, but you can also view the grids in the 3D viewer within VelPAK. And of course these grids can be moved back into Kingdom along with the TD curves generated. Okay, we will now move on to the second part of the webinar where I will briefly run through the VelPAK capabilities with regard to onshore complex structural traps where data is limited to 2D. I made a recording of these capabilities a couple of weeks ago, so I'm going to run this recording of the techniques available within VelPAK. However, note that the recording refers to our sister product Velit, which is exactly the same as VelPAK but available via IHS Market on the Petrel platform. In this demonstration I'll be showing how to snap test sections within Velit and demonstrating some of the snapping features. Now sometimes the geological structure cannot be easily represented by grids, which is why we use the snapping technique on 2D data instead when you have things like reverse faulted regions, salt intrusions, pods and channels. So in this case we get the profile mode depth conversion to work with the data, but before you can do the 2D depth conversion you have to go through the process of profile snapping. So data from workstation basically consists of segment orientated data and a set of a collection of digitized sequential data points measured by shot point and two-way time. Now, these points are collected into segments until there is a break in the data, which is usually caused by a fault, for example. Now snapping is the semi-automatic process that attempts to connect and integrate these discrete segment-orientated data into a meaningful geological layer. Once snapped, velocities can be applied per layer and the profile then depth converted. Okay, so I'm going to try and do this in real time on this first section, which shows a fairly complex section with an overhanging salt dome and various segments that have not been continuously picked for some reason. So if I press snap up here, the process has already read through and processed every event and has come up with the fact that the bottom layer has missing joins, so it's asking us if we want to auto segment merge this rather than us having to make manual merge options. So we say OK, and it's done it again. OK. This is another procedure. It is, well, I'll just press OK and zoom in, and then you can see what's going on. Now this event should be pierced by the salt dome, but the process can't extrapolate into the salt dome. It takes a extrapolation which would be taking us straight up there. So I'll use one of the processes here to move a point just slightly tweak it to go down into the salt dome so that when it tracks along it'll extrapolate into the salt dome and know that it's been pierced. Now if I reset and press snap again, you can see the process is tracking along each event, making a continuous layer for each event. Now it looked like it had finished, but it hasn't, because one of these events hasn't been picked on the left hand side of the fault here. So it's saying it cannot get back to the minimum shot point. So here we're going to, I just press OK, we're going to have to insert just a small amount of this event, which will take us up to the end of the section. So I need to pick the correct event. So it's event 6. Then I use segment insert, and I can just draw in that small portion of line. So if I reset, and now if I press snap, you see the entire section will be made up of continuous layers going across. And that's it, it's snapped, it's got fault uppers and fault lowers marked against where the events have gone up and tracked down faults. If I ask for a time fill of the section, we can see that each layer is continuous across the profile, and the colours of the layers correspond to what velocities will be assigned to that layer, which, if the layer is continuous across the profile, may be obvious, but in and around events where the events dip in and out of faults, and around the salt dome for example, it acts as an important QC to be sure the velocities are trapped in the correct layers. Now I'm just going to change the colour of one of those layers, because we've got two blues there, so if we just go and change the top thin blue to yellow, you can see clearer that it's a separate layer, although continuous over the profile, tracking down the faults. Well, that concludes the demonstration of snapping in Velit. It's clearly not something to be done on a 3D survey, and it can be quite time consuming, but I hope I've demonstrated that complex geological situations can be snapped in a way that a depth conversion can be run on the data. And it's fair to say that once proficient, you can find yourself picking the events and faults in the seismic workstation situation before moving across to Velit in a slightly different way, so that the snapping routines will work quicker for you once in Velit. Okay, now we will move on to the third part of the webinar, which is to look at the HiDef module and a brief overview of the theory behind it. So, HiDef can be used to scale processing velocities within a geologically constrained model and create hybrid models for layers where processing velocities may be less reliable. One common feature required of depth conversion velocity volumes is to add more detail so the volume may be used for a greater variety of uses, from better depth conversion between wells to providing a background geological model for seismic inversion, reservoir characterization, or bright or dim spot studies, for example. The HiDef tool takes a background model and adds the character of the sonic logs to that volume in a geological and geophysically consistent way. So the resultant velocity volume will still be accurate for depth conversions, tie the wells and retain the velocity gradient in the low frequencies of the volume, but with log scale detail. So it doesn't simply spread log velocity data between wells, but it uses the velocity trend in the input volume to propagate well velocities in a geophysically meaningful fashion. The geological constraints can be provided either in the tool or by importing an external geological model. Input velocity volumes may come from Kingdom dynamic depth conversion volumes, VelPAK velocity volumes, or any external seg-y velocity volume. The tool is easy to use and is highly intuitive for both geologists and geophysicists. HiDef uses kriging to distribute sample values from the sonic logs between layers taking into account the background trend from the supplied velocity model and the geological layering defined in each layer. The detailed velocities are used to depth convert each layer and a residual correction computed to ensure the velocities tie the formation tops at the wells. If data are unavailable over an area, it will blend the volume with the existing volume, and wells and layers can be individually selected and controlled. The residual error correction is then applied to the velocities using the same method as the initial distribution of sonic velocities to ensure a self-consistent volume. So, it provides a better volume for the depth conversion and is an ideal input for inversion studies, pore pressure prediction models, and reservoir characterization. Both these profile displays are from HiDef. As you can see from the traditional model in the top display, the standard velocity volume being displayed does not conform to the well information. Zooming into an area, you can see the well trace more clearly and that the velocity volume does not conform to the well information. Within HiDef, for each layer, the well velocity log data is detrended. For each log sample in the layer for each well, 3D kriging is used to propagate residual scalars using the background model trend, applying structural constraints defined for each layer in the geological model. Again, zooming in, you can see the velocity conforms much better with the well information. The geological behaviour of each layer is defined by assigning each layer one of 3 spread types: cut from top, cut from base, or stretched and squeezed. When the process is run, the layers are flattened onto a datum, processed, and then returned to the original layer structure. On this slide, you can see an example of the same profile with the geological behaviour of the middle layer having been changed within HiDef. The top display is cut from top. The layers remain parallel to the base but cut at the top. Zooming in, you can see the top velocity is drawn down to be parallel to the base of the layer. The middle profile displays cut from base. The layers remain parallel to the top but cut at the bottom. Zooming in, here the red velocity is remaining parallel to the top of the layer. The bottom profile displays stretch and squeeze. A well will be squeezed or stretched to fill the layer horizon regardless of the width of the layer. Zooming in, here you see the red velocity being stretched where the layer goes thick. As you can see from these examples, the volumes produced can look very different depending on which spread type you're choosing. Note that it is the user who is expected to have the geological knowledge of the area in order to make the correct selection of cut type. Just before we go in to look at how the program works, this slide shows comparative displays from within Kingdom between a dynamic depth conversion volume, a VelPAK velocity volume, and the more detailed velocity volume generated in HiDef. So let's move on to actually looking at the HiDef program. Here is a standard VelPAK screen. HiDef is accessed from the Tools drop-down from the top menu. Now we need to select the background model that we're going to be using, and HiDef will come up. The display starts with the surface map, similar to what you would see in VelPAK. Over to the left are 2 trees. One shows what is within the HiDef program. Initially it will come up with the wells from VelPAK, and under seismic trace you'll see the background velocity seg-y volume that has been read in. The model tree shows what data are available from the VelPAK project within the current HiDef project. For example, under each layer there are surface grids from the VelPAK project stored, which you can use later to do a depth conversion within HiDef. If we press the Well tab, we can see the HiDef display given the wells and the background velocity model loaded. The first well that is displayed is well 4814-2. These background colours you see are set randomly and denote the layers as defined from the VelPAK layer definition at that well. This first panel display shows the well velocity log in black, the velocity trend from the background velocity model shown in red, and the HiDef velocity curve, which is shown in yellow. The velocity trend from the background velocity model, which is the red, is from the nearest trace it can find in the velocity seg.y file. Panel 2 and 3 are diagnostic, showing how the depth is being worked out. Panel 2 shows a black line, which are the depths to add to the log to tie to the background model, and the depths to add to the log to tie the HiDef model, which is the red line. Note on the scale below the display that the red line should have low values trending towards 0 compared to the black line, as this well demonstrates clearly. The rightmost panel shows a cumulative depth error through the layer. The residual error is divided evenly on a per sample basis through each event. Going back to the first panel, the HiDef calculated velocity curve is in yellow. In this case, this curve conforms almost exactly to the well trace. This is because the HiDef smooth routine is off. However, smoothing takes place on the data before production of the final volume to reduce the variations of the well logs into general trends. We can view what the smooth trace would look like by toggling the smooth option on. This is done by going to the HiDef flyout and clicking the smooth active check button on and off. Look at the red curve on panel 2, which shows the depths you would need to add to the log to tie the HiDef model, and the yellow curve on panel 1, and see how they change depending on whether the smooth active is on or off. The smoothing parameters can also be changed in this panel. Smoothing is achieved by the Savitzky-Golay filter technique, which is a digital filter that can be applied to a set of digital data points for the purpose of smoothing the data, that is, to increase the signal-to-noise ratio without greatly distorting the signal. Here is a link on the screen for further information of this technique if you'd like to read more about it. The smoothing defaults are standard, and changing them will change the depths to add to the log to tie the HiDef model, shown as the red trace on panel 2, and will make it drift further away from 0. So you see that with smooth active off, the yellow curve in panel 1 lies almost exactly on the well trace, as would be expected. With smooth on, the yellow curve in panel 1 presents a more average picture of the well trace. Continuing looking at well curve 4814-2, you will see that there is a bad bit of curve around 550 to 600 meters per second, shown in the black trace. This may mean that you don't want to use the HiDef generated model for this layer, for this well, since the well trace data is bad. In which case, you can turn off the HiDef model for that layer, or for the whole well, and use the background model instead. This is done by going to the General flyout, finding the Well tab, going to the Well properties and selecting Use Background Model for layer number 1. You will see the yellow trace on panel 1 immediately move to lie on the red trace, since they are now using the same information. The red tie curve in panel 2 also changes for the same reason to conform with the black trace, since it shows the tie to the background model. Now let's look at the data as a profile by going into the Profile tab. 2D lines, 3D inlines, crosslines and random or arbitrary lines are supported as profiles. Let's display an inline that goes through a well within the model. Select the inline you want to display by going into the General Profile flyout. I'm going to select inline 5920. Pressing apply, a slice of the HiDef volume is being generated for the selected inline. So here you see the profile display and the two well logs that are near to the profile. Zooming in on the area of the profile near the wells, you can see that these tracks are showing the velocity well trace. The width of the colour bar associated with the well trace velocity is emphasised to make it visually clearer. Hovering over the well trace, it says how many metres away from this profile the well trace actually is. I don't know if you can read that, but it says 200 metres away. If we briefly go back to the map display and zoom in, The green line shows where inline 5920 is, and its proximity to the two wells that have traces that are on the profile display. Here you see that the high velocities shown in the wells in the last layer have been propagated through the layer, keeping the propagation parallel to the base. This means that this layer has been set within the HiDef tab as cut from top, as discussed in the presentation earlier. Now, to emphasize what HiDef is doing, in the flyout we will change the volume type option to the background velocity. So this will display the background velocity that was used within VelPAK to do a depth conversion. As you can see, the detail within the volume that HiDef produces is now missing. Another useful tool is from the general flyout to select the difference volume type. This will give you the difference between the background velocity and the HiDef velocity. Opening the colour table, and presenting it next to the profile, you can see that in the last layer there are differences between the velocities of plus or minus 1000 meters per second or more. If we have a quick look at the well panel for this well, 4814.4, for the bottom layer you would expect to see the same discrepancy between the background velocity model and the real trace and the HiDef volume. Going back to the profile, and turning it back into the HiDef volume, you can see how much closer the volume conforms to the well. Now let's take a more detailed look at the geological model parameters grouped and defined by each layer under the HiDef spread parameters. Each layer has a kriging range distance parameter and a spread type. The kriging range is the distance that the log propagation occurs. It defaults to cover the entire grid area, but this can be adjusted for specific layers. Looking at the spread type, you can see the three that has been mentioned before: cut from top, cut from base, and stretch and squeeze. And as we have already seen, we have the additional option of just selecting to use the background velocity model for any particular layer. Changing the layer spread type values randomly, then pressing apply, you can see instantly the changes the spread type makes to the HiDef volume. Here, for example, the base layer has been changed to be cut from base, which means the velocities will now run parallel to the top of the layer. It must be emphasized again here that geological knowledge is required to get these parameters correct for the layers in your own model. For more complex geological scenarios, such as reverse or complex faulting, it is worth mentioning at this point an external geological model can be imported from third-party software, such as LS Software's PaleoScan, and HiDef will propagate log velocities using that. If we go back to the map module, it is possible to draw a random line going through a number of wells by selecting the toggle button here and then clicking over the wells. A random line is being made, joining up through all the wells. Now if we go to the general flyout, the profile tab, select the line type as random and apply, a random profile slice is being processed, which we can look at in the profile mode when it is finished. And there it is. I'll change the scale of the display, change the well colour width bar to emphasize it. And there we have the perfect display, going through all the relevant wells in the project. All these features so far have been designed as QC tools for you to get the best possible high definition velocity from your data. Once you are happy with what the displays are showing you, the entire volume can be processed. It is easy to set up, but it will take a while to generate, so I won't do it now, but I will show you how. Go to the HiDef flyout and pin it out to hold it on the screen. In the 3D range, the output type is set to instantaneous, and that's the type of seg-y velocity I want to generate. Check that the output seg-y directory is set, and the name is set to instantaneous seg-y as your output file. The Run 3D tab allows a user to specify how many local CPUs are used for the velocity volume generation to maximize throughput on your machine. In this case, there are 8 processors on my computer, and I have set the number of tasks to be 8, so that all 8 CPUs on my computer will be used in batch mode to create the velocity volume that I want. Pressing apply will set the volume generation running, but as I said, I won't run it now because it does take some time to process. So as you can see, it is very easy to generate the HiDef volume and intuitive for geologists to easily add knowledge to the procedure. The resultant velocity volume generated is useful for depth conversions, petrophysical characterization and pore pressure prediction workflows, but the depth conversion of surfaces can also be done directly within HiDef. And an interesting way to analyse the volume you have just produced is to use it to depth convert your VelPAK surfaces you read into HiDef when you started the project. You can then look at the difference between the depth grids generated in VelPAK versus the depth grids produced in HiDef from the newly generated seg-y volume. So, to make depth grids or a number of other types of grids from the newly created seg-y file, we go to the Tools flyout. And the Make Grids tab. Here are the selection of grids that will be generated. If you don't want them all to be generated, just uncheck the box. Grids will be generated using the same AOI as the original VelPAK grids, and the kriging range is set per layer. Keeping the Apply Error box checked will mean the error will be applied per layer when grids are being generated. Finally, you need to select the input seg-y file name, which is what we have just generated, the instantaneous seg-y. Clicking Apply when ready will start the process of generating all the grids you have requested. When the process is complete, the grids will be available in the HiDef project tree. Here are all the grids that have been generated within HiDef. Closing the flyout and zooming in to the map, I'm going to select the depth for the first layer, and there we have on display the depth converted grid for the first layer within HiDef. As you may recall, we also checked the Apply Error box for the error to be applied every layer when we depth converted. This error has been stored and a grid produced of these errors in the Error Grid slot. Double-clicking on the error grid for layer 2, for example, will show you this grid. You can post the error values on the map too by opening the General Map flyout and changing the map posting type from None to, in this case, Error Before. As you may expect, the greatest errors causing various amounts of bullseyes can be seen over the wells. The reason we focus on the errors here is that now we have the error grids, we can use them to process the instantaneous velocity volume we have just run to produce another new volume which processes the error for each layer within it. Going into the Tools flyout and the Process tab, we can select the process type as being corrected instantaneous velocity. Check that the input seg y is the instantaneous velocity that we've just generated, and the output seg y file name prompts us the corrected instantaneous velocity seg y. Pressing apply will take some time, but it will produce the corrected instantaneous velocity volume. When the volume has finished generating, you can look at it within the profile using your random line that you've already produced on your map by going into the General tab and making sure that your line type is set to random. Specify the volume type as one that is produced by HiDef as opposed to the background model, and then select which velocity volume you want to look at. In this case, it'll be the corrected instantaneous velocity you've just generated. Zooming in on an area of this random profile near one of the wells, you can see how very well the profiles tie with the wells now that the instantaneous velocity has been corrected using the error grids that were generated. Once you have QC'd your new volume in profile mode, you can redo the depth grids within HiDef. Go to the Tools menu, Make Grids, and everything has been set up as it was. So press apply and the new grids will be made. Note the difference grids here. These show the difference between the HiDef generated grid and the original VelPAK generated grid. So if we click on the depth difference, it shows the difference at each point between the original VelPAK grid and the HiDef. You can immediately see that there might be some discrepancy here that needs looking at because there's a bullseye hovering over a well. So in HiDef so far we have made instantaneous velocity volume. We have produced depth grids from them which have produced error grids. We have from those error grids tweaked the instantaneous velocity volume to make a corrected instantaneous volume, which we are more than happy tie the wells. And now the only thing that remains for the HiDef process to be complete is to turn the corrected instantaneous velocity volume into an average velocity so that it can be read into Kingdom. This once again is done in the Tools option by changing the process type instantaneous to average. Select the output name, which will be, as you see, called instantaneous to average, and then pressing apply will produce the velocity volume that is needed to read into Kingdom. Right, this concludes the webinar presentation. If you have any further questions, please contact us on the email address support@equipoisesoftware.com or phone the telephone number on London office hours. And thank you for watching.